First of all, I want to make sure everybody's in the right place. So this is the second semester of astronomy. It's actually more of a intro to astrophysics and cosmology course. So anybody supposed to be in economics or something? Not supposed to be here? Okay. So I am guessing, I'm actually curious in general why you guys decided to take this class, before we even get going. I want to mostly today talk about what we're going to do in this course so you're in the right place. If you want to drop it, you can do so immediately before you invest any more energy in it. It's going to be a discussion-based course. I know there's a lot of us here. I don't think there will be this many of us a week from now. I'm going to spend a great deal of effort trying to talk you into dropping this class today, which is probably the opposite of what your other professors are doing. I just really want people to be here who actually care about this stuff and actually want to chop it up every week. And it's super boring for me. This is the third year I've taught this class. If I just stand here and tell you guys stuff, it's super boring. I have to do it for an hour and a half twice a week. So I want to be able to talk with you guys, and I want to hear your curiosities and what's gripping you about the reading and the videos we're watching, the crazy stuff I'm going to throw at you. Who here's taken any kind of astronomy in the past, in high school or at another college? Okay, a little bit. Anybody just watched some YouTube videos, and anybody looked at the sky before and wondered how things work, at least? Okay, fair amount of that. All right, so the really cool thing, there's a technical point here too. So usually we, the way that this has been formatted in the past, this course has satisfied some general education requirements. When we were back on, what was it called? The Strand system at SOU. It is actually now part of the Capacities program. So if you want Capacities credit for this class, you can talk to your advisor and make that happen. You do need to take the workshop alongside it too, if you want to get that GE credit for it. But I'm guessing most of you did not know that. Is that correct?
It's still G-Strand, right?
It is, but you can also get Capacities credit for it.
I don't know what that is. I'm a G-Strand girl.
Okay, well, if then you're grandfathered into it. For those of you, the point being that most of you probably signed up for this class because you were interested in the stars. Is that more or less true, or are you guys trying to satisfy some diversification credit for the most part? I mean, don't be ashamed. It's okay. I'm just trying to get a grip on who you people are. Yeah?
I thought the class was interesting, but I am here for a G-Strand.
Okay. And other G-Strand people here? A few of you? Okay, so fair enough. What's really cool, what I love about teaching this class and last semester is that y'all aren't scientists for the most part. And that's really cool because most people who aren't scientists have no idea how science works other than what they hear in the news media or something like that. It turns out to be a lot more exciting than what you probably believe from high school or something like that. In particular, this topic, because I don't think that there's any other field in science that's on the move as much as cosmology, astrophysics, and all the nitty-gritties that we're going to get into when we start looking at the sky. All we have when we look at the sky, unlike most science, we can't just do experiments, right? All we have is light from the stars. And so we can't run these nice little experiments where we, pit, different test tubes against each other with controlled experiments. We just have to look at what we see and then interpret that light and try to make a story that's compelling and gives us some explanation for what's going on. And the cool thing about that is that that story has been told for thousands of years, and it's always being updated. And I think that every single time we launch some sort of new telescope, which we've done very recently, we get a better picture of what's happening, and we have to really change our stories sometimes. I mean, just 100 years ago, we thought that our galaxy, the Milky Way, you guys seen the Milky Way at night? The little strands? Who's seen the Milky Way? Anybody? Yeah, that's the benefit of living out here away from the city. You can see the sky. We thought that the Milky Way 100 years ago was the entire universe, okay? Now we know that there's trillions of Milky Ways out there, of galaxies like that. That's how far we've come in such a short amount of time, and that's still changing crazily as we speak right now. So this is a really interesting and exciting place where we are going to actually get outside of the textbook. You guys have a free online textbook. Has anybody been able to access that already so far? few of you. Check it out. It's actually a really good textbook. It updates in real time, which is pretty cool. So sometimes I'll be flipping through it. I've actually been flipping through it and then reloaded it, and like the paragraph has changed under me, which is cool because they're updating to the best of their ability, the newest findings, and that can be really useful. But we're going to go actually far beyond that in the class. We're going to challenge a lot of the ideas that are in the textbook, look at different perspectives that might, have some friction with those ideas. And I think that that's going to make for a really exciting and hopefully heretical experience for all of us. What else do I want to say about this? So, like I said, a huge part of this class is going to be conversation. So I want to hear from you guys. And especially when you talk to me in these first couple of weeks, please tell me your name. I am going to keep a running list of attendance here. Attendance, oh, hey, David. Good to see you again. I think there's 2 people from last semester. That's awesome. I'm going to keep a running list of attendance. And so I will mark, I'll give you a little check if you talk, and I'm going to keep it running. At the beginning of class, I'll probably ask you guys for your thoughts about what we talked about last time. So hopefully you've had a couple of days to digest it. If you're not talking, I'll probably call on you and be like, what do you think? I might just read your name off this list I have here. It's going to be that kind of an experience. So if that terrifies you and freaks you out, you can drop the class. It's totally fine. You won't hurt my feelings. I do think it's really good for us to develop that kind of casual experience. For instance, just standing here and monologuing is really like unfun for me. And so I would much rather get to the point where we can discuss what we've been watching videos, reading in the textbook, and talking about in class. Obviously, we haven't had a class yet, so you guys have nothing to respond to, so I'll forgive you for being silent at this point. So let me make sure that you guys, any questions so far? Thoughts, concerns, terrors? No. So if you've had a chance to check out Moodle, and please do make sure that you can get into Moodle, because if you can't, you haven't registered for the class properly. Once you get into Moodle, you'll see that the class is set up in a pretty streamlined, simple fashion. So each week, usually on Monday, I will open up the next week's worth of assignments. They're all due basically midnight on Saturday, but in all honesty, I probably won't grade them until Monday. But you should try to get them in. You will have a short little 2-minute video response that you need to do each week, which is usually to a prompt. The first week is just introducing yourself so that me and the rest of you can kind of get to know each other a little bit. So you'll have a short little video assignment. There's a short little quiz over the reading material. That's important because we are not going to be doing the textbook in this class. And so I want to make sure that as I bring in some really far out, fringy stuff to this conversation, that you have had the opportunity to get the standard textbook explanation as well, so we can compare and contrast those. So those are the 3 biggest pieces of your grade. You got a little quiz every week over the reading. You got a video assignment. It's 2 minutes long. It's not going to break your back. And you've got attendance. So you actually have to show up and talk. If those things sound cripplingly difficult, then you should drop the class. There's also no final exam in this class or midterm exam, which is something that I'm perhaps starting to regret doing. But I hated exams when I was in college, and so I find them very stressful, and you forget everything by the next semester anyways. And so I think a better way of going about this is actually to have you guys do a small research project, and we'll get more into the details of that later. But I want you guys to really consider some things that you would never have a chance to otherwise. And so the research project is going to be built around examining some pinch points in astrophysics and cosmology where things are starting to take a turn in a completely different direction, or they have historically. So very similar to last semester if you were around then, except we were doing the solar system last semester. Anybody have questions, concerns, thoughts? Yes?
Could we do like a written version instead of the video?
You could. I would prefer it if it was in some way multimedia. So if you don't want to do, you could make a PowerPoint. You could record audio over top of it. If you're freaked out about cameras and lighting and all of that, it's totally fine with me. Likewise, if for the video assignment every week, if you, if you don't want to deal with camera and stuff, That's fine. You can use, there's a little audio recording option inside of that forum on Moodle too. Tell me your name. Ella? All right. Cool. First attendance point awarded. Yes.
I was going to ask about the video assignments too. What's like we have like kind of a quality check on those? Like how kind of perfect do they need to be?
Remind me your name. You told me. Tommy. I don't see you on here. You need to make sure that you are registered for this class.
I'm in the class on
You are? All right. I'm going to just add you in manually. So look, what I really want to see you do is, this first week's a little bit of an exception because you're introducing yourself. What I really want to do is see you thinking about something or wrestling with something. I really think that, that's what I'm trying to do too when I teach this class is wrestle with something. So I want to bring up some issue for me that's like really troubling with the reading or troubling with some news headline about cosmology or astrophysics. And I want you guys kind of do the same thing. Find the things that are weird to you and wrestle with them in these responses as much as you can. And like the technical details of how you perform that are not really so important to me. I really want to see you guys not necessarily doing what you think you're supposed to be doing, but really struggling to make sense of something. And it's okay if you don't get to the bottom of it. We'll sort it out in our discussions, hopefully. Or we'll at least get closer by the end of this semester. So, yes?
Regarding the video submission, I don't know.
Tell me your name again.
John Stone,
Okay.
last name.
Yep.
I don't know if the file size for turn-in is maybe set low, but I noticed that you said max 2 minutes, 2 minutes or under. I think when I got to 36 seconds, it shut down and was like file size too large. So then I had to go real fast, and I don't know if that's going to be a problem.
Interesting.
Like maybe micro videos.
That's weird. You might reach out to the IT people here. That shouldn't. I'm sorry. Yeah. I mean, another way that you could do it is you can record on Zoom. Like you can just start a meeting because you guys all have access to Zoom through the university. Record a meeting that's 2 minutes long and upload that. You should be able to get away with it. If that doesn't work, you can upload it to your drive and share the link with me. Just use my email address and share the link with me. But nobody was having trouble for the most part last semester doing 2-minute videos. So it sounds like I can help you later if you want. If it's still a problem, there's a really wonderful lady who heads up the IT department and this dumb stuff, and we will figure it out. Don't worry. Yes. Tell me your name. You've been in one of my classes before, no? Yeah. All right. Welcome back.
For the videos, are we doing that third-party source to upload the videos, or are we doing it on Moodle?
We're doing it on Moodle now. We used to use Flipgrid, but Microsoft ditched it. So that was shocking and unfortunate, but yeah. Yes. 100%, yeah. So the workshop, you guys, I haven't really touched on that yet. Who here signed up for the workshop, first of all? Most of you. All of you. Most of you. Okay. The workshop's actually really cool because we don't have an observatory here, obviously. This isn't a university with a professional astronomy department. This is a virtual observatory, and it's actually really cool. You get the opportunity through the exercises to kind of do everything from fly around the solar system and the galaxy to measure the distances between things. You can even run it back in time. You can go check out the stars on the day you were born. It's a really cool module. So I recommend everybody does that. It costs $30 to buy this software, but I think that it's well worth it. Probably the cheapest lab course on campus, even at that. So check it out. Let me know if you have problems getting into it. And occasionally somebody has an issue and we have to go through the whole IT hellscape, but it will be all right in the end. Yes, tell me your name. Yes.
I have 2 questions. So how do you get into the workshop? Because when I was getting into this course, I didn't see a workshop when I registered for this class.
I believe it's Physics 115, PH 115. Check it out. Yeah, you can add it, no problem at this point. Just talk to your advisor.
Is it required for this though?
It is if you want to get GE credit for the course, basically. Yeah. Anybody else? Yes, tell me your name.
I'm Liz Pizarzik, PAS. First name will be Liz.
Got it.
So for the workshop, is that like separate from this class? Will we be discussing that in this class, or is that kind of an assignment?
It's not. I mean, we will not be talking about the workshop assignments in this class. It will give you context for what we're talking about in class. Much of the Moodle stuff is to be brought into the discussions, but I really want this to be an open conversation of a class. So yeah, in so much as it's useful, relevant to our conversations. Yes. Yeah, in the back. I do not have you on my list either, sir. Make sure you're registered. Is it a point system? Yeah, it's a point system. So you will get immediate grades back from the quizzes that you take. By the way, if you guys, you probably haven't figured this out yet. If the quizzes, you can take them as many times as you want. This is actually a selling point for this class, is like, there's no reason that every single one of you can't get an A in this class. It is not a difficult class, you just need to do the work. So the quizzes, you can keep doing them over and over until you get all the right answers. You can, I'm basically, like I said, I'm grading the video assignments based on effort more than anything really. Honestly, same with the final projects to some extent. So there's no reason for everybody not to succeed. The only people who don't are the people who don't do the work. And that's a lesson you gotta learn, I guess. It seems like a huge waste of money. Good Lord. It seems like a huge waste of money to take a class though and not do it. So make sure you wanna do it. This is a good moment to figure that out. Yeah. Interesting. Has anybody successfully bought the software? A couple. Talk to me after class. Let's see what's up. You said your name was Cecilia? I didn't think that I have you on my list either. Oh, I do. Okay, fantastic. Lucas. Other questions about these technical stuff? Yeah. No, it's fine. Courtney, hello.
But just to clarify about attendance, if we typically talk in class, but there's like a certain day that we don't, we get marked absent.
You do, but I am recording all of these. I will upload them to YouTube. I'm completely off of I was going to show some slides for all of this, but I have a YouTube channel just for this class, so I will upload the lectures. If you are going to miss a class, like, guys, if you get sick, if you're like just stuck on the toilet all weekend or something, don't email me about it. Like, I'm not a doctor. I'm not that kind of doctor. I can't help you with that. Just watch the lecture. Send me a short, send me a deep thought that you had about it afterwards. Something that demonstrates to me that you were wrestling with something inside of it. And I will mark you down for being present that day.
How is the workshop, how is it gonna work? Like, are you just gonna give us like,
Yes.
can you see if you can find this type of star in the sky, take a photo of it, send that in?
Yeah, what was your name, by the way?
Aiden,
Aiden. So the workshop, make sure I have you on here. I do. The workshop is like, it's really a series of exercises. Was anybody here, David, did you take the workshop last semester? Levin, did you take the workshop? Can you say anything about exactly what the sort of problems are that are on the workshop? Yeah, it's online, but like what kind of questions, what kind of exercises were there?
It's like date back to this date, see where this star was, tell it the exact coordinates of where it was located. And then I was like, can you go to this galaxy and tell me what's located directly this direction?
Yeah, there's
Following along, it was like not setting you up to at all. It's like you look at the questions online, you answer it right.
Yeah, it's a lot of like measure this, measure that, but also it relates it to some of the concepts that we're going to get into, like how do you actually determine the distance based on parallax versus based on some other methods that we're going to get into. So it does relate. It's more of a practical expression of the concepts that we'll be discussing both in the textbook and in class. Actually, in class, we're mostly going to be picking fights with the textbook, but it will, in some sense, round out our survey of astronomy. So, yes.
Is the
Tell me your name again. I'm sorry.
Isabella.
Isabella, that's right. I already got you. Okay.
Is the astronomy workshop, software, is it by month? I can't remember.
No, I think it's just a one-time purchase. Yeah. In the back.
I'm
Mia, hello.
Throughout the workshop, will it all just be through the software, or is it observations as well?
It's all through the software, yeah. We don't have the opportunity right now, unfortunately, to do anything in person. Plus, you guys would have to get up in the middle of the night, and you probably wouldn't enjoy that. Yes?
I'm not too sure if you already answered this, but how do you get into the workshop?
You have to buy a subscription to it, essentially. It's like a year-long subscription. It's linked on the workshop Moodle. What was your name, by the way? She. All right. I don't think I have you on my list here, by the way, Shay. You are. Technical details. We'll figure it out. Yes.
Sorry, I had like
You
two
good?
clarifying questions. So for the workshop, if we're just in it for like a gen ed, it just fills a point for that. We don't need to be in the workshop and still get credit, like it's.
I think that you do for the either for the strands program or for the capacities. You
I
need
don't
to.
know if the strands are at all, I don't know. Anything.
So you know about the capacities thing?
No.
Oh, goodness gracious! Talk to your advisor. Make sure you're getting the credit that you need. It's worth it. It's a very easy workshop points, and it will, I think, help you get a better grip for how people have come up with a lot of the data that we're going to be using as a foundation for the conclusions we try to draw from it. So it's worth doing. I don't think it'll take you a lot of time. Yeah.
That's exactly what I was gonna ask, is how time consuming is it? Because I already have like a lot late, but it sounds helpful.
I think the workshop probably take you, I don't know, let's ask the people who took it last semester. How long did the workshop lessons take you guys? We just lost one. 11, what do you think? Half an hour? An hour? There you go. Yeah, a week, something like that. All right. Any more technical or related thoughts on the top of your head? They will pop up. Raise your hand as we keep going. I already did most of this. Yeah, so today I really wanted to just do the course, the syllabus. I want to introduce myself. I haven't really done that yet, so I probably should. And then, depending on how much time we have, I want to start talking about light and solar structure. The beginning of our journey starts with the sun, because the sun is the Rosetta Stone of all of astrophysics and cosmology. It is the perfect tool, if we can understand it, to unlock everything else, because all the other stars are unbelievably far away. It's actually difficult to comprehend how far away they are. But we have a really nice one sitting very close to us that we can actually survey. There have actually been spacecraft sent all the way out into the solar atmosphere. I've actually had the pleasure of talking with a number of the scientists who worked on that mission too. So I'm going to try to bring some of that experience to this conversation. But the sun is where we're going to start. And so depending on how much time we have today, we'll start into the sun. It might seem like we have everything figured out about the sun, but the truth is, well, it couldn't be farther from that, actually. There's some really interesting changes happening to the way that we understand the sun. It is not what we thought it was, and a new model is emerging for what is going on with that thing. So, anybody know what cosmology is? Yeah. Yeah, what's the cosmos?
I'm just going off the etymology here. I know.
It's okay. Cosmos, anybody heard that word before? Yeah. I mean, it's close, yeah. Anybody else? Yeah?
I'm not going on it much, but like more like beyond our like solar system, beyond the Milky Way. So like planets, solar systems, like galaxies farther away from ours.
Yep, these are all appropriate uses of the word. Anybody else? So that word cosmos, it's actually a Greek word. It's usually used by the ancient Greeks in opposition to this other word that you've probably heard before, which is chaos, right? Everybody probably knows you guys know what chaos means, right? What's chaos? Disorder. Disarray, right? So, oh, you're good. So if cosmos is the opposite of chaos and chaos is disarray, then the Greeks had this idea essentially that cosmos was the order, right? It is the ordering of all of this madness into something that is sensible and makes sense. So that's ultimately, I could imagine having taught this course, like last semester we did the solar system. This semester we're going to do the stars, and eventually we're going to build towards this story, which we call a cosmology, right? And the cosmology is our best attempt to order literally everything in the universe into a coherent story, which might be a fool's errand on its face, but it is something that people spend an inordinate amount of time trying to do. And, you might think, by the way, they've been trying to do that forever, it turns out, right? So this idea of developing cosmologies has been central to every single culture on Earth, indigenous, imperial cultures everywhere on all the continents ever since the beginning of recorded history and way before that as well. And it's really interesting because traditionally speaking, cosmologies have been associated with mythologies, right? So when most people, for most of human history, let's say anatomical human beings have been around for, 300,000 years or something like that, we don't really have any idea what the heck people were up to before the last ice age, right? But even in the last, let's say, if we go back to recorded history, maybe 6,000, 7,000 years, people are looking up at the sky, and what do they see? Well, they don't see what we see today, even though technically they're perceiving the same balls of light and everything like that. In other words, they have no conception that, planets are giant orbs of rock and gas, right? There's no ideas like that. They're actually seeing these representations of their world up there. And they give them these mythological stories. They associate the planets with gods. They associate the stars with gods. And you might think like, this is like really primitive and superstitious, and these people just didn't know what they were doing. But it's actually quite a bit different than that. And we're going to unpack some of these mythologies in this course too, because they're actually really profound stories that these people were reflecting in the motions of these bodies above their head. And something that's really interesting is that cosmology wasn't a real hard science until about the 1960s in the West here. So cosmology has traditionally been this place where we tell stories about the universe. And after, let's say, moving into the modern era of the West, cosmology became kind of the purview of the church, right? So the origin of the universe, where everything comes from, where everything's going, what's the purpose of everything. That was traditionally a theological domain until really, really recently. Actually, until the 1960s, and we'll get into exactly what happened there. But the point that I'm rambling about is that what we're going to try to do with this course is come up with a story that's sensible for the evolution of what we see in the sky. And I think that word evolution is really critical to the new way of thinking about these things, right? So, when I was a kid, there's this really popular idea that the universe was born on one fine day, it had a birthday a while ago, about 13.8 billion years ago. And everything sort of proceeded in this linear fashion. And one day, as things from this explosion drift apart, the universe will end in this abysmal heat death, right? That was that's been a very popular story for, I would say it's been a very popular story for about 50 years, and it was a popular story before that. And actually, if you go back before people were even looking through telescopes, it was a popular story then too, right? So this idea that the universe hatched out of an egg of some sort goes all the way back to the Sumerians. It goes all the way back in many indigenous cosmological stories as well. And of course, it's reflected in the Judeo-Christian tradition with the Genesis story. And so this idea is not new, that the universe popped into existence one day. The problem is that today, not today, but a couple of years ago, we plopped this really powerful telescope at a nice little point outside of our orbit, where it can sort of hang out there, and we pointed it at the farthest reaches, the deepest parts of space, as far as light will possibly reach. And it's been a little bit troubling, I think, for the whole domain of fitting that story to the data. Because what people see when they look back to the earliest moments of the universe is not some primordial, ball of goo, right? And this requires a little bit of preamble because, of course, when we look really far away, well, the light from really far away has taken billions of years to travel here. And so in a sense, we're looking way back in time when we look far away. Anyways, when we look back there, we don't see this primordial goo. We actually see fully formed galaxies that are astonishingly mature. And it's really troubling, actually, and it's really upsetting the entire discipline right now because we're in need of a new story for what's going on. Now, that new story might be, some sort of repair job on the old story, or it might be a completely different story altogether. But unpacking what's going on with that is going to be the goal of this course at length. And it all comes down to understanding what the heck that light means that we're seeing from far, far away. And the best way to understand that is with our own sun that's right here. Did somebody have a question? Yes, thoughts?
Like, do we go into that in this course?
We will go wherever you want. We will go into that if you want. So, you mentioned quantum. So light, right? The production of light. This is really important that we understand what light is. And I don't mean just in terms of the equations that govern how light behaves. That's generally as far as most science classes go with it. I want to go deeper than that, actually. I want to try to understand how light is produced and what the heck it actually is. Because it's clearly something that atoms are doing. It's clearly an activity, right? So we do in this course, it's a little bit of a dualist approach that we have here. On one sense, we have cosmology, which is the stories that we're telling, right? So the story is kind of the fundamental unit, the kernel of knowledge by which humans transmit information to one another. You come home at the end of the day, you're talking to your roommate or your spouse or whatever, and they're like, what happened today, right? And you tell them a story. And that's how they come to understand anything. That's how we all understand stuff. So on one hand, we have stories that we tell about things. On the other hand, we have physical hard reality. And we're going to assume that physical hard reality, just like the Greeks and the Sumerians before them, and really the Indian subcontinent astronomers from antiquity and the Chinese, all sort of assumed that physical reality could be broken down into little pieces of stuff. And the Greeks called it the atom, right? And so we're going to assume that physical reality does produce the phenomena that we observe, and that we can essentially trace that back to some action or activity of atoms. Now, we're going to have to tell a story about that. It's going to be necessarily incomplete, and it's not going to encompass everything in the universe, right? If I asked you to explain to me, why you love your parents, or hate your parents for that matter, you probably wouldn't bring atoms into that story, right? So there's a huge part of the universe that has nothing to do with atoms, actually, and I think that's really important to remember as we talk about cosmology. The cosmology that's popular today, the physical cosmology that the scientists are in charge of today, it's really devoid of the kind of wisdom that our ancestors valued when they talked about cosmology, which is largely about how the heck you're supposed to live, because living turns out to be really complicated and difficult. So the stories that we tell in cosmology these days are about atoms. And so, yes, we can go down we'll definitely end up wrestling with some quantum physics. Not in a mathematical sense, but in a sense of what the heck does this possibly mean? But that's only part of the story, right? And so I hope that in this course we can explore both sides of what a cosmology should look like, what a productive cosmology would look like, because I don't think a physical cosmology is all-encompassing. It's only half of the universe as far as I can tell. Yeah.
Talking about stories, so are we gonna see this perspective of every nationality explaining the beginning of our solar system and stuff, and even then, are we gonna talk about the Big Bang, solar death?
Oh, yes. Every nationality? Probably not. So I'm limited a little bit in language, right? So you'll have to forgive me. This is definitely a Western-centric course. I'm going to be leaning heavily when I go back in time on the Sumerians, who are the root of the West. The Greeks followed from them. There's a little bit of contribution from the Egyptians and the Canaanites. I will be referencing some indigenous cosmology stuff from our local area and from the Navajo. I have not been able to penetrate Eastern cosmology as well. There's a huge language barrier with accessing the Chinese internet, so that whole world is like very difficult for me to get into. I can get into some of the Indian subcontinent, so ancient India as well. Again, I don't know if you guys realize this, the ancient Indian script, the Indus Valley script, has not been decoded. It's actually really phenomenal. So we do have access to Sumerian writing. We have a tremendous amount of it. But around the same time, perhaps even earlier, there was a whole civilization developing in the Indian subcontinent, and we can't crack the code of it yet. So we don't really know what's going on there, but there are some interesting pieces. So yeah, we're gonna try to glue all that together as much as we can and get a bunch of different perspectives on it. Again, there is so much, like, when I asked you guys what the cosmos means, several of you were like, basically everything, right? So this is in some sense a course about everything, but we'll ground it in the physical cosmology, which is obviously the popular approach to cosmology in the modern era. But we'll also see how that seems somewhat incomplete. And so I want you guys to understand how all of our ancestors thought about cosmology in a very different way than the scientists today. Yeah.
So we're going to be talking about kind of the mythos
Oh yeah.
surrounding
Now and then. Yeah. What's your name?
Geo.
How do you spell that? I don't have you on my list. I gotta get a better list. Yeah, I know. I only have 24 people on my list, so there's definitely more than 24 people here. Hopefully, y'all will remain next to us. Okay, so yeah, so that's it. I guess what I'm trying to say is that in some sense, this is definitely a course, and particularly when it comes to the textbook, when it comes to the workshop, it's pure physical astrophysics and cosmology. It's not brutal math. You don't need to know how to do second-order differential equations, but it is definitely rooted in atoms for the most part, right? So like I said, the reason attendance costs so much in this class is because I want to not do that 100% of the time. I think it's really important we talk about other aspects to it, and we talk about challenges to the various atomic proposals, because I think even those are falling short in many really interesting ways. And when we start talking about the sun, you'll see what I'm saying. So we will be coming at it from all these different perspectives. And if, guys who were around last semester, we did a fair amount of that as well. So, questions?
I might have one.
Yeah, yeah.
Where those two kind of split in the 60s, where we took science on one hand and mythos on the other.
Yeah, I mean, so astrology is, first of all, no stupid questions. Let's just eradicate that right now. If you have a question, I guarantee you somebody else is thinking it, or at least will be very soon. So don't be afraid to talk. Astrology is a really interesting situation, right? And of course, astrology was deeply tied up with astronomy for most of human history. So the idea that you could, the Sumerians actually had an entire class, like an ethnic class of people called the Chaldeans, who were essentially their court astronomers. I mean, these were people who had their own portion of the town in ancient Babylon, essentially, who would inherit this skill of astronomy from generation to generation. And their job was to advise the king, essentially on whether it was a good or a bad day to do X, Y, or Z, to go to war or whatever it might be. And it's interesting because it turns out that making predictions based on the locations of stars is not the best way to plan your investment portfolio or something like that. It actually turns out to be pretty bad at that. But in the process of doing all of that work, they amassed incredibly accurate star records. And so we can actually go back and when we run these simulations in reverse, we can find the different events with incredible precision that people, 8,000 years ago were writing about and making these star catalogs. So in the 1960s, something, we'll work towards this, but something really interesting happened, and it was the discovery of this phenomenon, which is called the cosmic microwave background radiation. And I don't want to get into that today, But that essentially turned this Genesis story of the hatching of the egg, the Big Bang, into a legitimate scientific theory. I have some serious doubts about whether the cosmic microwave background radiation is cosmic at all, but we'll get to it in due time. So something really interesting happened. I think for now it's most important for you guys to realize that cosmology was not a hard science. It was definitely not in the physics department prior to the 1960s. It would have been something you'd see in like a theological or a seminary school or something like that, maybe philosophy to some extent. Nietzsche played with it a little bit, but came up with very different conclusions than today's cosmologists. Thoughts? Yes.
Can we discuss maybe the potential, just extraterrestrials in general, and then maybe their potential involvement in our evolution for the theorized one?
Yeah, we had a little more time for that last semester, but I'm definitely open to it, and I would like to hear your guys' thoughts as we get into it. In so much as it's relevant to, I think it's an interesting way to interrogate how large this place is, because you can get into some really interesting statistical arguments about, why don't we see lots of other people in the stars, people really believed that we would. Actually, people were thoroughly convinced all the way up until a couple hundred years ago that the other planets were occupied, right? There was actually a big debate in the very serious Royal Society minutes about these Solarian creatures, people, let's say, inhabiting the area below the sunspots. This was back, I believe, in the early 1800s, so not that long ago. And people honestly believed that there was life on Mars until the 1970s, when we actually went there. You could actually, has anybody seen Mars through a telescope? A little bit. You can actually see seasonal changes on Mars. So it actually gets a little bit, it looks kind of greenish is the thing. It gets little dark patches on it in the winter. And people thought for sure that it was growing stuff on it until very, very recently. So people have been progressively shocked that we're not finding more people out there. And we'll get into why that may be, despite the fact that there may be lots of people out there, why we're not seeing them. Yeah.
On a similar note to what else is out there, will we be at all discussing sort of multiversal theory or what's beyond our universe?
Yeah, we can play with that. We can absolutely play with that. I mean, absolutely. Yeah, the important thing I think to realize before we start getting into too much, okay, so all of these ideas depend on building upon primary observations. So we look up at the sky, we see that there's something moving around in the sky, and then we make up a story for what's up. Now, the story that our ancestors made up, a gazillion years ago, about it being a god in the sky or something, completely reasonable, actually, on its face, right? Because who's going to say it's not, right? But we need to understand why people don't think that that's the case anymore first, because once we understand how that primary information, again, all we have is light. That is literally all we have. Maybe we can go taste the sun with a spacecraft at this point. But for the most part, everything we see and that we're going to talk about comes down to interpreting observations of light. And so as long as we have a good grip on that first, and then we can start to grip why people have constructed this cosmology that they have, then we can start to play with alternative interpretations of that data, different proposals to explain how the cosmology can be rescued in the face of intervening facts as of late. There's a lot of places we can go for once we get closer to it. But I think that the first few weeks, we're really going to just try to understand how stars work, honestly. Not that anybody 100% understands how stars work, but we do have some stories that might be helpful. And we can see problems with those stories too, which also might help us interpret the bigger story at the end of the day. So, questions? Yes. Tell me your name.
This is sort of off topic.
Tell me your name. Can you tell?
Sandra, sorry.
Sandra. All right.
Cassie.
Gotcha.
Do you know any good news sources or media anywhere that is about stars or that you think is accurate about learning about any of this stuff, that you think is more accurate?
I do, and I spend, so this is not my primary job, so I actually have a lot of jobs, but one of my jobs is I run a podcast with my wife, who's also a scientist, And we're getting slightly out of order here. But I am constantly, this is, by the way, the website for if you want to listen to the lectures that you miss. I linked it in the Moodle too, so you can get to it in a second. Let me just skip ahead here. We have a podcast too. We're constantly talking to people who are pushing the edge of a lot of these ideas. We don't just do astrophysics and cosmology, we do everything under the sun, honestly. We've been doing a bunch of economics lately because economics is impenetrable, and I really wanted to understand it my whole life and haven't, so we've been calling up economists and making them explain how things work in the money world. But we do everything, consciousness research, different philosophical topics, ancient history, everything. So I do encounter a lot of really interesting people, and I will be pointing you towards as we go through. And I tried to add different links in the Moodle to stuff that I think could be interesting. I inherited the Moodle from a different professor before I took this job, so a lot of the links are from somebody else, but I'm trying to add my own as I go through each year. So if there's a topic that you're like, I want to know more about that, ask me, and I will point you towards something. Especially some of this stuff as we get off the beaten path and we get away from the sort of NASA narratives and the textbook narratives. We're going to have to, by the way, narrative, just a synonym for story, right? It's a story that we tell, and there are lots of stories to be told about any situation. So yeah, check that out. So let's see here. Tiny bit about me. So I actually, my background is all over the place. I worked for many years in different forms of biological research before I ended up going back and doing my PhD in a biophysics realm where I actually studied the weird way that molecular water behaves under tension. And the lab that I worked in, this is at Columbia University in New York, we actually ended up making these little machines that were powered on evaporation, which is pretty cool stuff. And you might think, it's kind of weird that there's a guy who's, basically an expert in water physics teaching me about stars. Sort of true, sort of not true though, because the fact of the matter is that atoms are responsible for the light, which we are going to use to make sense of the entire universe. And so we have to understand atoms and we have to understand light, and I have a great deal of time invested in that. Another project that I'm going to be bringing into this is the material atom. So who here, you guys have taken like intro physics, intro chemistry? Anybody? High school chemistry, physics, a little bit? You guys probably, studied some model of the atom that was like, there's like a nucleus here, and there's like these little electrons that fly around in circles around it and stuff like that. Okay, this is essentially like, anybody ever been to New York City before? This isn't probably a good example. You guys seen those subway maps that they have on the walls of the subway? They're like, not at all like actual maps of the city. They just kind of tell you where things go. It's kind of like that. This is like a wiring diagram for the atom. It's by accounting accurate. It will allow you to build pieces of technology in a constructive way. But nobody on Earth actually thinks this is what an atom looks like. Now, what's really funny is that very few people are really even concerned with what an atom looks like, or what the heck it's doing, or what does it even mean for some part of the atom to have a positive charge versus another part of the atom to, say the electron cloud that's zipping around outside of it to have a negative charge. What does charge mean even, right? These are really, really interesting questions to me. And I'm actually, along with my wife, we're in the process of publishing a book about this right now. I'm going to be bringing these ideas into the class because it's really important to me that we actually have a physical representation of the atom that's functional so that we can imagine how the atom does crazy magic like gravity, like magnetism, like light, like electricity. How does the atom actually pull these off without just maddening magic? Because what we're given otherwise is a bunch of equations for how it works, how it functions, how it goes down. They're essentially descriptions of what's up, but they don't actually give us any idea about the atom. So I'm going to be bringing some different material representations of the atom into this class as we go ahead as well. It's kind of like this. If, this is the way that essentially that modern science is portrayed, which is wonderful for building machines, by the way. It's just not very good for actually understanding the nitty-gritty. So if I was to, have my, let's say we all went to a magic show, and there's a guy on stage, and this woman gets in a box, and he just starts sawing her in half, right? And I asked all of you guys, to tell me what happened. And I let's say I could even record, like I gave you each a camera, and we could reconstruct the event from every angle in the auditorium. We would have this magnificent picture of this woman getting sawed in half, right? And this is sort of like how we do atomic physics in the modern day. We have these incredible equations that describe exactly what the phenomena looked like. But at the end of the day, the woman didn't get sawed in half. It just looked like she got sawed in half is the thing. The reality of the situation is that behind the box, she just pulled her legs up, he sawed through the box, and everything went on as normal. So the mathematics that we are satisfied with for a lot of this basic physics surrounding the atoms, surrounding light, electricity, magnetism, gravity, it's very functional because it allows us to make these representations of reality so that we can build technology. But we haven't really figured out or even spent much time at all trying to figure out how the heck the guy sawed the woman in half in the first place. Of course, he ended up not sawing her in half, but it looked like he did. And so that's going to be a huge piece of what we're wrestling here with, which is what is the difference between a description of what's going on and an explanation of what's going on? That's a huge, huge broken piece of the way that we approach a lot of these problems. And it's something that we all need to start thinking about really hard, because it's very easy to take a description of how something went down as if it was an explanation, particularly because descriptions are so technologically useful. You get an equation, you can engineer your way into incredible technology, like these cell phones and computers, and these lights and all of this. They're all done by essentially watching that woman get sawed in half and reconstructing the scene with numeric representation, right? Doesn't mean that we have to have any idea what actually happened or what the atoms were doing to each other, physically speaking. So this is where your quantum physics is going to start to become a real essential piece of the story sooner than later, probably before the end of this class. So anyways, we'll be playing with the material atom, which is a very revolutionary idea. What else? Questions about that? All right. So let's start talking about the sun a little bit. Now, this is a very beautiful picture of the sun. I hope that this is coming through all right for you guys. One of the things you'll notice just stare at this while I tell this to you. So your textbook tells us about the sun like this. It says, the consensus understanding of the sun, this is actually the first line of the first chapter in your textbook. It says, the sun, like all stars, is an enormous ball of extremely hot, largely ionized gas shining under its own power. Okay, so this is the standard picture that we're given of the stars in general, is that they're these big balls of gas. Something's happening. It's not quite, we can't quite think of them as like combusting. They're not burning like a candle exactly, but they're having some sort of nice exothermic reaction, and they're giving us all of this heat and light, and it's good because we couldn't live without it. Now, what's interesting is that by treating the sun as this ball of gas, it allows us to imagine a whole path of possibilities, right? Because gases are really interesting forms of material, right? You can squeeze gases, right? You can disperse gases. Gases can do all sorts of incredible stuff. Now, that's a lovely story, first of all, and that's the story that we've had for about 150 years now, is that the sun is a ball of gas. Now, there's one fatal problem with that story, actually. And it's something like this. So, by the way, what does ionized mean? Because part of that sentence was ionized. A huge ball of ionized gas. Anybody? Ions? Got a chemist in the room? What's up? Yeah. Anybody else? So you said separation of positive and negative charges or something like that? Okay. Yeah. Yeah, it's lost or gained electrons. Again, these are all very nice accounting ways of thinking about what's going on. So generally speaking, a gas is inert. So you have a bunch of gas. It does not, generally speaking, conduct electricity. However, when you pump that gas down under pressure, so you vacuum most of it out of a tube, let's say, we call it a vacuum tube, right? Actually, these light bulbs above our heads, I don't think they're LEDs. I think they are gas bulbs. They're very much the same process right now. So they're very low pressure, like they've been vacuumed out of most of the atoms, but a few. And all of a sudden, when you vacuum something down like that, the atoms become what we would say is ionized. In other words, they become conductive. They can conduct electricity for some reason. And I think we'll circle back on why that is once we get a better material picture of what the atom actually is. But needless to say, the sun is supposed to be under a similar condition where the atoms, the gaseous atoms, are ionized so they can conduct electricity. Now, there's a serious problem with this proposal, though, and it's probably the most interesting thing that I can introduce you to today. If you never come back to the class on Thursday, this will still be wonderful for you to hear, I think, in so much as I think that the scientific revolution starts with this primary realization, which is absolutely mind-bending if you can see it for what it's worth. So I need to start actually bringing a prism to this first class. You guys you played with prisms before? Dark Side of the Moon? You guys know what I'm talking about? Basically, a piece of glass where you can split light into its corresponding wavelengths, right? You could use a garden hose too in the sun, right? You've sprayed some water. Maybe you've seen a rainbow, right? So when light travels through different mediums, essentially different wavelengths are relayed through that medium at different rates, and you essentially get a spreading out of the colors, right? And we're going to get more into this process because it's essential for interpreting what we see in the sky. But let's start with a very simple situation. If you take a solid or liquid and you heat it up, right? You've perhaps seen this. Has anybody ever been to like a glass blowing studio or something like this? Anybody been to like a blacksmith or seen like a glowing piece of metal before? A couple here and there. Maybe like you've seen lava in a movie at least, or maybe you've seen it in real life. Anybody seen lava in real life? Oh, that's awesome. I've never seen it. Really want to. Anyways, if you go and put your prism in front of something that's glowing hot, what you will see is that it disperses the colors into this beautiful rainbow, right? It's actually, it's essentially known as the Newton spectrum, but it's a rainbow for all intents and purposes. A rainbow is the Newton spectrum. Now, if we were to look at, let's say, the colors versus their intensity. So this is like intensity this is a graph I'm going to make for you guys. Intensity on the y-axis, and the colors, we'll call it wavelength over here. Each color is associated with a wavelength of light. We'll talk more about what that means later. For any heated body, what you get is a nice distribution of colors versus intensity. This is completely generic, and it applies to any heated body or liquid in the universe that we know of. Anytime you heat up anything, you actually will get this curve. It's called a black body curve for reasons that we don't have to get into today, but I'm happy to elaborate on the initial experiments. Actually, I think we'll get to it later this week. So this is quite interesting. Now, what happens if I heat up a gas, on the other hand? So let's say if I pump down one of these tubes and I put a current through it. It gets really hot. I put some electricity through it. What does this look like for the gas? Anybody? Anybody know the punchline here? What kind of do we get all sorts of different wavelengths out of it? No, actually, if we were to take a prism and hold it up to this light right now, I bet we would see 3 colors, red, blue, and green. And they would be perfectly tight. there would be exactly that frequency. So with gas, we actually see these individual lines. There's literally little spikes of color, just a few different exact colors that mix together so that we have something which vaguely approximates white light, although I find it not to be in any way as satisfying as actual sunlight. Sunlight. Now, the weird thing about sunlight is almost a perfect black body spectrum. It's actually one of the most perfect black body spectrums that we've ever seen. Now, it turns out that there are some little lines overlaid on the sun as well, because the sun clearly has a gaseous atmosphere around it. You can actually even kind of see that in this picture. There's clearly something rarefied in the outer limb of the sun, in the outer portion. But what's really troubling about this whole picture is that the sun, were it to be, as your textbook says, a ball of ionized gas, well, it should look a lot like this, not like this. So this might seem like it doesn't really matter too much. Well, as we move downstream from this fundamental chaos that's at the heart of solar physics, we will see that not only does it matter, but it really matters, because when it comes to interpreting what happens to a star as it evolves, the story that you tell when the star is made out of gas is very different than the story that's told when it's made out of condensed matter of some sort, right? Condensed matter like the table or the water in my glass over here, which give us this nice black body spectrum. Very, very different outcomes. Now, if that's not enough to satisfy you for why it matters, and you can wait, till we're a few lectures deep into this before you decide whether you care about that or not. How about fusion power? You guys heard about fusion power? So fusion power is this wonderful promise that we can avoid the dangers of nuclear fission, traditional nuclear power. We can avoid emissions. We can avoid basically everything that sucks about trying to power our civilization if we can figure out how stars do their magic. How is it that stars generate all of this heat and light? Well, most people would agree that stars are one of the best candidates for where new atoms can come from. And the way they make new atoms is they squish some simple atoms together and make something more complex. That process of squishing in two little atoms together and making something more complex gives off a little bit of heat, a little bit of light, a little bit of energy, essentially. It's a relaxing process. But it takes an enormous pressure, the furnace of a star, to make it happen. So what we're trying to do in the laboratory today, not me personally, but what scientists are trying to do is replicate what they believe is happening inside of stars on Earth in these little machines they're not little actually, these big machines they call fusion reactors, right? Where they're trying to replicate the process. Now, how's that going? It's not going well. It's not going well. And actually, every few years, there's like a headline that comes out that says, oh, we're making huge gains, I saw the most recent one, making all the headlines on the different mainstream podcast stories, we had net positive gains on this process. We generated, so many millijoules of energy from this thing. Then you start to go and you actually read the white paper about what's happened. And the fact of the matter is that they actually put 400 times the energy of that nuclear fusion process into the laser to power the reaction in the first place. They don't tell you about that, right? So my point is that it's not going very well, this process of trying to develop nuclear fusion power. Now, you could say, why is it not going well? Anybody have any idea why it's not going well? Just technically speaking? Anybody read about this at all? Yeah, why is it difficult? Do you remember? The difficulty is that they're taking a ball of gas and they're trying to squish the ball of gas from all sides in such a way that the atoms will be forced into each other and fuse and make... And look, it is possible to do that. They've demonstrated that it's possible to do that. The problem is that it is so unbelievably difficult to confine that ball of gas in a vacuum. The way they do it is with really, really powerful magnets, essentially. And then they try to focus this laser beam on them and squish them all together at once, right? Because in their mind, this is the I guess it's about 100-year-old story for how stars power themselves, is doing this gaseous fusion. It was developed by this gentleman named Arthur Eddington back in the 1920s. Now, prior to Arthur Eddington, the entire scientific community was losing their freaking minds because they could not figure out how stars were powered. They tried to explain them in terms of being powered like a coal furnace or something like that, in terms of gravity. They tried everything on, and I'm going to go through some of these old models. The problem was every single one of those solutions resulted in the sun burning up in a matter of a few million years. And they knew that wasn't sustainable because all of this really interesting archaeology was coming out around the same time about, people were discovering dinosaur bones and things, and they were starting to realize for the first time, this was in the 1800s, by the way, they were realizing for the first time that the Earth wasn't just a few thousand years old, that it was probably millions of years old. Now people think that it's billions of years old. Some people think it's trillions of years old. So people were really having to reconsider how in the heck the sun could do this. And this guy came along. He made this very compelling argument using the ideal gas laws that you all probably picked up in high school for a second anyways, about how this fusion process could happen under gas pressure between atoms. And we've inherited that story, that the state equations have been inherited all the way down from Eddington about this gaseous sun, right? Now, that would be nice if it were true. The problem is that the sun gives us an unambiguous black body rainbow. And we have never, in all of our efforts as scientists on Earth, been able to generate a black body spectrum from a gas in a laboratory. Can't be done. You cannot actually take a gas and squeeze it or do anything with it or ionize it. There's no way to make this kind of light turn into a black body spectrum no matter what you do. And so for me, it seems like, and for a number of other scientists, this is stuff you're not going to find this in the textbook, but there's a huge revolution underway in terms of thinking about what the sun actually is. Because this story that we've been telling for so long, which is informing our technology, our approach to fusion, our approach towards interpreting the flickering stars that we think are dying in distant galaxies, interpreting the distance of distant galaxies and the edge of the universe, all of these things depend on us believing that the stars are simple gases that have been ionized. And it's just an increasingly untenable proposal. So that's going to completely reshape all of the conclusions that we're inheriting from the previous generations before us. Because now that we're actually trying to build these fusion devices, we're starting to realize that that doesn't work. Not only does it work, but we probably can't keep lying to ourselves about this black body situation as well. So that is sort of at the heart of what I think that I want to unpack, and I'm not sure that I want to go too much further than that today. Does anybody have any clarifying questions about this piece of information that I'm trying to put in your lap right now?
Maybe yes, no, but are there preeminent theories about what the sun can be if not gas that are already out there, have been out there, or is this just starting clear?
Yeah, so we have a really good sense of what atoms the stars are made out of. They're mostly made out of hydrogen and helium, mostly hydrogen. Turns out so are a lot of the planets. So Jupiter, basically made out of the same stuff in the same proportions as a star, right? There's obviously some difference, right, in that the star is big, there's a lot more of those atoms, and so it's able to crunch down and do this fusion process. But yeah, in terms of, so, this isn't exactly what you asked about, but it's worth mentioning that NASA has actually experimented with a different approach to fusion technology. There's only 2 papers that I'm aware of, and actually I've actually tried to reach out to these scientists that were on this paper, and they kind of brushed me aside and sent me through. I've talked to lots of people from NASA, so this is really weird, and that is kind of exciting for me because I think they're actually onto something, and they don't want to talk about it. They've actually published a paper on a different type of fusion approach. And the way that they do this other kind of fusion is they impregnate a substrate with these fusible atoms. So they'll take some sort of like deuterium, some sort of really heavy hydrogen, a really simple atom, but it's kind of already got a little extra weight to it. So it's ready to be fused really nicely. They impregnate a metal of some sort, a very heavy metal lattice with those little fuel pieces. And what they found is when they do this, instead of trying to confine this fuel, this hydrogen fuel mixture inside of magnets in a gaseous form. When they put it inside of a lattice and they squeeze it with just a little bit of laser light, so we'll get into this later, but light has momentum. You can actually squish stuff, push stuff around with light if you want to. They can actually do this at ambient temperatures. They don't need these huge, expensive fusion reactors. They don't need really high temperatures. And the power gains are more or less on the same equivalency with just these very early couple of experiments that they've done with this method. And they have nothing to do with using a gaseous situation. It's actually based on sticking atoms inside of a lattice of atoms that already exist there. So we'll play some more with potential ideas for the actual material composition of the sun, but what I really want you guys to start realizing today is that the material composition of the sun, not just what atoms it's made out of, but on what form those atoms are existing in, really could change not just the stories that we're going to tell about the cosmos, although it certainly will do that, but it really can change our approach to technologies that could honestly make our lives a lot cheaper and easier here on Earth, which is ultimately what people want. Thoughts, questions, concerns? Yes?
How do we measure like the ions like on sun or on other stars? Because we can't really measure it because like the sun is too hot and it probably melts.
All we have is light, right? And I'll break that down a little bit more for you in terms of like, we'll look at the solar spectrum and we'll try to make sense of what the different lines on it mean. And because we're going to keep doing that with all of the stars. And as we look at some distant stars and we say, oh, this star is in this stage of its life, well, why do people think that? It really comes down to what they believe a star like our own is capable of doing. And so that's why I really want to, I'm going to go slow here. I want to make sure that we really understand the ups and downs of the sun before we get too far away from the sun, because if we can't understand the sun, or if we've misapprehended the sun so terribly, then everything that we tell downstream of that is going to be equally affected by it. Now, I also don't, I want you guys to understand, this is awesome. This is how science works, okay? Every few hundred years, people look up at the sky and they're like, holy crap, we were at everything completely wrong, actually. And that's great, because every time that happens, then we have the opportunity to leverage it towards new technological achievements. Maybe it's just part of what it means to be a human and understand the world around you. Science is never done. It's always something where people are going to continue to fight about it until every little detail makes sense. And even then, people will argue about what the details mean. Yeah.
The new method of fusion that they're investigating.
Yeah.
Does it still have to do with magnetic confinement, or is it just based off the lattice and like?
Yeah, if you guys want to Google it, it's called lattice confined fusion. There's a couple of white papers about it. I think we're going to be seeing a lot about it in the coming years, to be honest with you, based on how squidgy the people were that I tried to talk to about it. Yes?
So earlier you said that the scientists determined that the universe probably billions, maybe trillions years old, because they're trying to replicate a model of the forming continuation of the star. Correct?
It is a story that's told that is congruent with the story of the sun that we have. So we work out, or that short, perhaps.
Yeah. But what about with the new stars that are typically younger and will expand themselves quicker, that are really going to be maybe
Yeah, I mean, right, so galaxies are believed right now to have multiple generations of stars within them. Now, this is, we'll go in with the luxury of detail through this entire story, don't worry. So we have plenty of time for that. This only becomes troubling when we turn our telescope to the earliest galaxies that we can see that are really a couple 100 million years after the supposed beginning of existence itself. And those galaxies look fully mature with population, with fully mature stars that have high metallicity that couldn't have actually been first generation stars. You actually end up in a situation where you're really pushing the timelines. That's where things start to get a little more dicey. in that situation. In terms of following the state equations that give us this story of the lives and deaths of gaseous stars, it's totally reasonable that a blue star that's enormous would burn itself out rather quickly, like you say. But we'll go through that story a bit. I think that this argument here was something of a big argument in the Royal Society back at the end of the 1800s. Ultimately, they didn't have access to a lot of the information we have today. One of the key pieces of information that they didn't have access to was what happens when you put hydrogen under extraordinary pressures. So, perhaps some of the guys who were in the class last semester will realize, but maybe some of you guys have heard of this too. Jupiter. Have you guys heard about the interior of Jupiter? Has anybody heard any whispers about what the heck is going on inside of Jupiter? So there's this new idea, right, that Jupiter is made out of the same stuff as the sun. But as you go down into Jupiter, it's really interesting because they do these like cross-sectional, sort of like this, kind of cross-sectional pictures of the planets, in the textbooks. And over the years, really recently, that story about what the interior of Jupiter looks like has changed radically. It used to be this ball of gas, and then there's like some rocks at the center. Now, what we believe Jupiter is primarily composed of a liquid metallic form of hydrogen. It's called liquid metallic hydrogen, which is interesting because, and we'll have to talk a little bit about what it means to be a liquid versus a gas. But, needless to say, liquids actually have structure. They have a very transient structure to them. But, water, when it's under pressure, it actually has a layered-like structure to it. You can actually feel, and I've been around some of this work. I worked with this very particular kind of sensor when I was doing my PhD. You can actually push through each one of the layers of water when it's under pressure. So it actually forms this shell-like structure under pressure. Turns out hydrogen does the same thing, and it's called liquid metallic hydrogen. Now, the people who came up with this gaseous sun back in the late 1800s, they had no idea that liquid metallic hydrogen was even possible under pressure. Just didn't occur to them. Not only that, they didn't have the technology capable of generating the enormous pressures to actually observe it in the laboratory and actually recognize that, hey, wait a second. Nowadays, we've actually created liquid metallic hydrogen in the laboratory by subjecting, by basically pulsing little specimens with enormous pressures, like gazillions of pascals of pressure for an instant, such that we can actually observe the change in the properties and these transient lattice structures. The point that I'm getting at is that this idea of the gaseous sun is more than 100 years old. It's really outdated. It's like an old creaking ship that's got a bunch of holes in it that are being plugged from all directions. And there's some really interesting stuff that's coming online. And it's going to absolutely change everything about the stories we tell downstream. And I think it's going to absolutely change how we make electricity here on Earth in the future as well. So that's at the heart of all of these downstream threads. The things that you guys asked about were, we will address all of them. I want to make sure, please, if you didn't talk in class today, that's cool. Do come up afterwards. I'll let you guys go here in a second. Please come, tell me your name, introduce yourselves so that I can mark you down. The admin wants to know who didn't come to the first day or the first week of class, I guess. But in the future, yeah, when you guys come back on Thursday, hope I will see you again. If this is not your cup of tea, that's totally fine. Make sure you spend your time studying things that you love. It's too short not to. Otherwise, hopefully we'll see you guys back here on Thursday, and we'll continue this journey.